Okay. We have the last lecture on inflationary reheating today. It's about phenomenological application of reheating. I think it's very interesting and hot topic for recent years. So please, Marcos, start.
Okay, well, thanks again, everyone, for being here. I hope you don't get too disappointed regarding today's lecture, because you can say many things about the phenomenology of reheating. So for the first lecture, I didn't really have time to go to finish and talk about warm inflation, but in any case, the slides are going to be posted in the Indico webpage, so you can have a look. I put some references in there. Yesterday I didn't have too much time to talk about the primordial black hole production during reheating, so that's another hot topic today. Honestly, I didn't have a lot of things to say regarding PBH formation, but I think for anyone interested in the topic, again, I put one or two references there maybe. Because according to the people that are very knowledgeable on this topic, you can produce primordial black holes through the parametric resonance, essentially. So not only the fluctuations of the fields grow, but essentially overall density fluctuations grow during reheating, and they can collapse gravitationally eventually if reheating lasts for sufficient amount of time. So today I'm going to focus mostly on CMB, the connection between reheating and the CMB. And I'm going to talk as much as I can about dark matter phenomenology that is connected also with reheating. So let me start right away. For the CMB part, I think it's a good idea to remind everyone of one of the first slides that I showed in the first lecture, which is this feature of inflation, and which is where its predictive power rests, which is its ability of leading to a relatively scale invariant power spectrum of curvature perturbations. Okay, so as I mentioned before, because of this accelerated expansion, a quantum fluctuation in field and metric can be stretched out to become a classical perturbation that can lose causal contact with itself. It freezes to the horizon crossing value until it re-enters at much later times during radiation or matter domination. Now, for single field inflation, which is the case that I've been studying so far during these lectures for, let's say, lack of time and also lack of generic results, the gauge invariant fluctuations that one can construct correspond to the scalar curvature modes and the tensor modes. Okay, so the scalar curvature modes here, I am writing them in terms of the in the Newtonian gauge in terms of the metric fluctuation and the scalar field fluctuation. Although I'm writing it in a Newtonian gauge, this combination is gauge invariant, so this is just a scalar perturbation, a scalar quantity, for which a power spectrum can be defined in Fourier space. Okay, so you take the two-point correlation function and you obtain a power spectrum of these fluctuations. This Dirac delta function is there essentially because the uncorrelated nature of these quantum fluctuations that lead to this power spectrum. For the tensor fluctuations, you can do the same thing. So these tensor fluctuations are primordial gravitational waves. If you add over polarizations, you can also compute the corresponding power spectrum. And one quantity that is very important, that is phenomenologically relevant, is this ratio, the ratio of the power spectrum of tensors to the power spectrum of scalars, which is known very originally as the tensor to scalar ratio. Okay, so it's denoted by this little r. This plot down here is showing just one example of how a curvature mode freezes in value as it crosses the horizon during inflation. So time in this scale is running from right to left. So this power spectrum evolves inside the horizon, and after it crosses the horizon, well, very shortly after it crosses the horizon, it freezes to a constant value. Okay. What else? Okay, for multi-field models, you can identify more scalar, well, more gauge invariant scalar modes that can be excited, and these correspond to isocurvature fluctuations. But currently, there's no proper detection in the CMB, and I'm going to just limit the discussion to single-field models. Okay. Now, because of this freezing out property of the fluctuations, the computation of these power spectra in the single field models is a very simple exercise. Okay, in the inflationary plateau, if you remember the shape of the potential that I showed at some point, every Fourier mode essentially follows approximately the same expansion history. And so the power spectrum that one obtains is approximately scale invariant with a deviation that is parameterized by some tilts that are denoted in the scalar case by ns and in the tensor case by nt. Okay, so one can compute the power spectrum in terms of quantities evaluated at horizon crossing for the corresponding scale that one is studying. And then, as I said, these power spectra are approximately scale invariant. So the tilts, ns and nt, you see are defined in a different way. For the scalars, if ns is equal to 1, the spectrum is scale invariant. For the tensors, if nt is equal to 0, the spectrum is scale invariant. So this is just an odd choice that was set in stone some time ago. And what this plot is showing is the reconstructed form of the power spectrum by Planck around the Planck pivot scale, which one can see is almost scale invariant. I mean, it has some tilt, but you can see this tilt is distributed in some way across several decades in the wave number. Okay. So from the Planck observations, from the CMB observations, one can put constraints on the tilt and the tensor to scalar ratio. But before doing that, one needs to understand how to connect a fluctuation that one observes in the sky with its inflationary origin, okay? And to do that, one needs to know the history of the universe between the moment this fluctuation here, for example, oh, sorry, let me explain this axis. So the horizontal axis is just the size of the universe, the scale factor. The vertical axis is the size of the comoving horizon. Okay, so if we set a particular comoving scale, in this case, I'm showing the present horizon scale, then to connect to understand the connection between these times and early times, one needs to know, as I said, the history of the universe between the moment this fluctuation left the horizon during inflation and the moment at which it re-entered the horizon. So this the rightmost side of this plot is, of course, very well known. We know that we are currently in the lambda-dominated era. In the past, we were in the matter-dominated epoch, and at higher temperatures, we were in radiation domination. As for inflation, we know from the first lecture how the comoving horizon shrinks due to the exponential expansion. So essentially, the gap in our understanding of this plot is precisely the duration and the nature of reheating. Okay, if we know the precise duration of reheating and the slope of this line, we will be able to state exactly how many e-folds of expansion before the end of inflation, so before this point, a particular scale would have left the horizon. Okay, so that's the meaning of this n star. If we choose a comoving scale k star, this n star tells us how many e-folds pass from this point to this point. Okay, and so this is just a drawing. Let's say mathematically we can compare a given pivot scale to some, which, as I said, is denoted by k star, with some, let's say, what's the word? Some reference scale. Okay, so one particular reference scale that one can use is the present moving scale, determined essentially by the current measurement of the Hubble parameter. At horizon crossing, this scale is of the same size as the comoving horizon. Okay, and in turn, we can relate this ratio with the number of e-folds after horizon crossing, as I said, from this point to this point. And so yes, so we replace this A star by A evaluated at the end of inflation. And in turn, this ratio can be manipulated to be rewritten in terms of, as I mentioned, the number of e-folds after horizon crossing, the energy density of the universe at horizon crossing, where is that? Here it is, H star, and the energy density at the end of inflation, okay, and at the end of reheating. So here I'm denoting, you see, I'm not using the subscript reheating, I'm using a subscript rad, because what we want is the energy density when radiation nomination begins. So all I'm doing is rewriting this, ratio, as I said, in terms of energy densities evaluated at this point, and at this point, okay? So rho rad applies from the moment W becomes equal to 1/3, all right? So this is a horrible expression, but one can actually almost solve for n star, okay? And the connection becomes a little bit more transparent. So these n star, after evaluating some of these constants, let's say in particular the present Hubble scale, sorry, these ratios, for example, one can obtain an expression that looks like this one, okay? So n star is equal to some number that is of the order of 60, 70, a term that depends, of course, as I said, on the relative size of the pivot scale and the reference scale, parameters evaluated during and after inflation, and most importantly, this bit here, the one that concerns reheating, which depends on the energy density at the beginning of radiation nomination, the energy density at the end of inflation, and this parameter W int, which corresponds to the E-fold average equation of state parameters. So that is defined here. Yes, W int is this. So W varies, even if it's slightly, it varies during reheating from this point to this point. And this W int is just its E-fold average. Okay, so we average in time, but instead of using cosmic time, we use the E-fold variable. All right. So concerning reheating, then the effect on n star is going to be that, for example, a smaller energy at the end of reheating, that is a longer duration of reheating, is going to require more E-folds of inflation for a given particular scale. Okay. And so, as I said, these E-folds depend on the slope of this line, and that slope is precisely quantified by this parameter W int. So what we would like to do is to see the effect of this, of reheating on the CMB observables, on the observables that we can measure in the cosmic microwave background. So as I mentioned at the beginning, I think, maybe I didn't, but in any case, any constraints that we can impose from CMB observations are going to be model dependent. Maybe I can go back a little bit. So you see the power spectra in particular depend on the velocity of the field and the energy density during inflation. So of course, if you choose a particular potential, you're going to get one result. If you change the potential, you might get a different result. So these constraints are necessarily dependent on the model. So for models, just to let's say, just to showcase this dependence on reheating, I want to choose a family of very well-known inflationary potentials, which are known as the alpha attractors, okay? Two of these families are known as the E models, or as the alpha Starobinsky models, and the T models, okay? So the idea here is that depending on a parameter alpha, which is here in the exponential and here inside of the hyperbolic tangent, the corresponding potentials can be deformed to have a very narrow or a very wide minimum, okay? For the E models, which are exponential, there's only one inflationary plateau where slow roll occurs, whereas for the T models, there are two plateaus, so slow roll can happen on either side of the minimum, okay? The importance of the variation of this width relies on the fact that horizon crossing for the pivot scale that we choose can occur on top of the plateau or below it. And since the velocity of the field is going to be different depending on the slope, the observables are going to necessarily change and depend on the value of alpha. Now, to emphasize, alpha equal to 1 is a special value because for the E models, it reproduces what is known as the Stravinsky model of inflation. All right. And I didn't mention anything here explicitly, but another thing that makes these models compelling is that they can be constructed from well-motivated supergravity completions of the standard model. That's all I'm going to say about supersymmetry. But it turns out that for these two attractors, evaluating n star, the number of epochs during reheating, turns out to be surprisingly simple. Okay, so notice that I am talking about quadratic potentials, by the way, sorry, quadratic potentials at the minimum. So we can make use of the expressions that we derived in the first lectures to evaluate these portion of the expression for n star that depends on the duration of reheating. Okay, and the idea is to use the expression for the radiation energy density that we wrote, that depends on this integral with respect to the scale factor, and the fact that the scale factor can be computed in terms of the energy density of the universe at the end of inflation and the cosmic time. Okay, so we are in a matter-dominated era, so A is approximately going like T to the 2/3, but if we keep the prefactor and we use this expression, we can convert this quantity into this quantity, we can substitute and obtain this extremely, I mean, this is a very simple result that is conspicuously missing in most of the literature. I don't know why, because this is a very simple connection between n star and the dynamics during reheating. It just depends on the log of gamma of phi, the decay rate of the inflaton, which here is approximated as a constant. We have k equals to 2, and the Hubble parameter at the end of inflation. So, for example, for the E models, one can explicitly substitute things in the expression for n star. At the Planck pivot scale, so the Planck satellite uses a pivot scale that is equal to 0.05 inverse megaparsec. At that pivot scale, we can evaluate n star, so n 0.05, and we can almost solve it in a closed form. Okay, so we get n star is equal to this number. This bit that depends also on n star, it is 1/3 of the natural log of the effective Yukawa coupling that we use for the decay of the inflaton, and the effective number of degrees of freedom. If you want, you can solve this expression in terms of what are known as Lambert functions, but it's better to just plot it, okay, as a function of the coupling or equivalently as a function of the reheating temperature. So here I'm showing results for alpha equal to 0.1, 1, and 5. Okay, 1, remember, is the Stravinsky model of inflation, and you can see that as long as if you pick, if you have a definite UV completion of the standard model, if you have a definite particle model of inflation, you have to pick the strength of the coupling between the inflaton and matter. That is, you pick a particular value of the reheating temperature, and that immediately selects a value for n star, which is equivalent to a value of the scalar tilt computed for the power spectrum. Okay, so if you fix reheating, you fix the predictions on the CMB. All right. And of course, the same is true for the T model. Here, the expressions are slightly different, as you can see if I switch back and forth, okay, for n star, but for ns, they change more. You see, here's 0.965, now it becomes 0.963, just because the shape of the potential is different, right? So with this,
excuse me, what is y?
What? Sorry?
Why is the y? This is small y.
Oh, yeah. That's one thing I forgot to write down here. So why is the effective Yukawa coupling? If you remember from previous lectures, this gamma phi, the decay rate of the inflaton, was proportional to the square of y. So I'm parametrizing things in terms of an effective Yukawa. It doesn't have to be a decay into fermions. It can be a decay into other particles. But yeah, this gamma phi is y squared divided by 8 pi times the mass of the inflaton. Okay, so sorry, I forgot to make this connection explicit in here. Yeah, okay. So, okay, before I go ahead, I just want to make a small note on the case k bigger than 2 when the potentials are not quadratic. In that case, as we saw in the first lecture, in principle, you can approximate the equation of state during reheating using the oscillation, the anharmonic oscillation of the inflaton. For k equals to 4, this W is equal to that of radiation domination, which means W int is equal to 1/3. This whole thing just cancels out. So we get 1 minus 1. So there is no dependence at all on the duration of reheating. And you always get the same value for n star, which is approximately 56. And maybe you remember these plots that I showed last time. So you see, as a function of the coupling, n star is completely flat for k equals to 4. Okay. So that's something to keep in mind. If you have a model with a quartic potential, there is no room to play with n star. It's always 56. If you have k bigger than 4, in principle, this expression would predict that n star can be bigger than 56. But as I mentioned at the end of yesterday's lecture, this is very dependent on the interactions because the inflaton condensate can be destroyed and you cannot use this expression for W, okay? Also notice that this is kind of a transition value. You see, for k equals to 4, we have 56. For k equals to 2, we can at most get close to 56, but we're always below it. All right, so that's something to keep in mind. And as I said, with this at hand, we can now see what the CMB has to say regarding reheating, at least for these particular models, okay? And I thought it would be interesting to see the connection in a historical context, because the last few decades have seen the early universe cosmology turn from a almost qualitative science into a precision science. We can do now precision computations thanks to the development in part of these new ground-based and extraterrestrial observatories, among which I want to emphasize the roles of COBE, WMAP, and Planck, which have mapped the CMB to an ever-increasing precision. Okay, quantitatively, I think I want to begin with the latest WMAP data release, which occurred in 2012. In this plane, I am mapping the predictions for the E models and the T models. So E are the continuous curves, T models are the dashed curves, okay? From very small alpha, passing through alpha equal to 1, which is this orange line, all the way to formally infinite alpha, which corresponds to the prediction for inflation with a purely quadratic potential, okay? Now, as it is generically done for now, I am not specifying the reheating temperature, and instead I'm showing results in the range between 50 and 60 volts of inflation after the pivot scale crosses the horizon, okay? Horizontal axis is the scalar tilt, the vertical axis is the tensor to scalar ratio, and WMAP uses a different pivot scale than Planck. So one has to be careful. The pivot scale here is 0.002, okay? So it's always a good idea to put it explicitly. And the dark blue contour is the 1 sigma allowed region, and the light blue one is the 2 sigma contour, okay? So we can see that even 10 years ago, quadratic potentials were starting to be in tension with the data, but there was pretty much no constraint on the width of this band, which would constrain reheating, okay? The next data set corresponds to the first data release of Planck, which happened in 2013. Now, for reasons that I still don't fully understand, maybe someone can actually clarify this, the Planck team decided to use their pivot scale for the scalar measurement, but they kept the WMAP pivot scale for the tensors. So these two axes have different pivot scales for some reason, okay? And this is confusing. There's actually papers where a lot of people miss this mismatch, okay? Because you have to compute the observables twice. You have to solve twice for n star. But the important thing to notice in any case is how much better the constraints are, in particular on scalars, although they're still not great, right? For the second data release, which is that from 2015, the allowed region has shrunk dramatically and it has moved a little bit to the right, you see? Quadratic inflation is essentially ruled out, and Starobinsky inflation with 60 equals more or less hits the bullseye. Qualitatively, the same thing can be concluded from the last Planck data release from 2018 with an even smaller amoeba, let's say. And we can see that the width of the blue contours and the width of the dumbbells start to be comparable. So we can now think of extracting constraints on reheating. And this is even more true after this last December data released by the Bicep and Planck Observatory. So this one is from December, and you can see we have much better constraints. So now we can blow up this picture and actually compute things appropriately using the connection between, as I said, reheating and the number of EFOLs. So to the left, I show the predictions of the Emodel accounting now, as I said, for the coupling with the standard model in terms of this effective Yukawa coupling or in terms of the reheating temperature, depending on what is more convenient. And what I want to point out here first is that a reheating temperature that is as low as that during BBN, which is a few MeV, this inflationary model would be very, well, not completely, I guess, because this is just 2 sigma, but it would be disfavored by the data, okay? Even reheating temperatures of the order of the electroweak scale fail to enter the 1 sigma region. So you see, we can use the CMB data to put constraints on reheating given one particular model. Now, this pink band in here is the preferred range of temperatures in the supersymmetric version of the model, and we see that in terms of the Yukawa coupling, it goes all the way to 10 to the minus 5. Again, 10 to the minus 5 is showing up as it always does in any reheating computation. And in particular, only values of alpha between 1 and 12 register points inside the 1 sigma region. In fact, the bullseye is only hit if we allow the Yukawa coupling to be as large as 1, okay? One thing you should note is that I'm showing a region between 1 and 10 to the minus 5 shaded in a different way. It has a hatched field. I will mention that why that's the case in a minute. But before doing that, we can now turn to the right and look at the D models and see that we can get similar results, except that the disfavoring of small reheating temperatures is even stronger in this case. So BBN is all the way to the left, completely disfavored by the data. Reheating temperatures of the electroweak scale order are also disfavored, and inside of the 1 sigma region, we only have in the preferred supersymmetric range only values of alpha equal to 1 to 5. So very disfavored, let's say, if we don't want extremely large couplings between the inflaton and matter fields, okay? And here, before going into further details, I need to mention a little bit on the meaning of these contours. These contours were computed by the Bicep-Keck collaboration, as I mentioned, making a few assumptions. They assumed a fixed lambda CDM baseline that corresponds to that of Planck. And they, in particular, take a fixed reionization optical depth, okay? And for some strange reason, they didn't combine the Planck constraint on R with their own constraint. So there is no correlation of tensor modes between Planck and Bicep for some reason. And the assumed tensor spectrum is scale invariant again. So that's what they do. So very shortly after these results came out, an independent team released their own set of constraints, also in December, which according to them is better because it accounts for the correlation between R and tau. It combines the limits from Planck and Bicep on R and uses consistently the single field relation for the tensor tilt, And also, which is a bit more important to me, is that they use the same pivot scale in both axes, you see. So in any case, I am not saying these contours are better than the other ones. That is to be determined by people who are experts on extracting data from the CMB. But you can see that for these new constraints, the bound on R, the upper bound on R doesn't change too much, but NS is shifted a little bit to the left, you see. So smaller reheating temperatures fit better in the blue region. Although the bullseye seems to still being hit only by very large couplings, okay? So now I need to specify why I'm hatching this region, right? Why I'm saying this is not the favored region for the supersymmetric models in particular, but also because the things I mentioned before may or may not apply during reheating. And the thing is that we partially know the answer. We know that if the couplings are bigger than 10 to the minus 5, we have to worry about non-perturbative particle production during reheating, which might change the simple relation that I wrote before that was extracted from the perturbative picture. In particular, in terms of the equation of state parameter, I showed yesterday this plot that tells us that if we have an inflaton strongly coupled to a scalar field during reheating, so preheating, then the equation of state parameter can be deviated from the matter-dominated value. So it can take values that are close to those of radiation domination momentarily, and therefore the presence of this modification of the equation of state parameter will modify the prediction in the region that is seems to be preferred by the CMB observations. Unfortunately, at least for myself, for us, this is still work in progress. I am sure that people, well, in fact, I looked a little bit at the literature. There's people that address this effect, but there's not a lot on the quantitative side, okay? So if you ask me what is the answer, how these contours are, well, not contours, these lines are modified, I don't have an exact answer yet, but all I wanted to give you is a hint that CMB data, at least for these particular families of inflationary potential, seems to point toward the presence of non-perturbative particle production in the early universe, and you need to do the hard work to extract CMB observables, okay? So this is if we have scalar preheating. If the inflaton decays primarily into fermions, one can also track as I mentioned yesterday, the energy densities and relic abundances non-perturbatively, but remembering the previous lecture, the non-perturbative dynamics results in a suppression of the energy density relative to the perturbative approximation in the case of large couplings. And so even if there is a large initial peak in the energy density, it becomes very quickly suppressed, implying that for fermionic preheating, there won't be any measurable effect on CMB observables at all. The equation of state parameter during reheating is not going to be affected, even if we have non-perturbative particle production, unless we make the coupling extremely large, for which, you know, not even this applies. You have to actually now worry about fermionic back reactions. So that is a much more complicated problem, because as I mentioned, there are no lattice codes for fermions available. So that is a very complicated thing to explore. So this effect has yet to be determined. But I want to emphasize this because what's written in the literature is that if you have y bigger than 10 to the minus 5, you also affect the CMB observables. That is not true. You don't affect them unless essentially you modify when reheating happens. And that only happens if your coupling is of order 1 in the case of decays to fermions. There is another reason why one has to treat the large coupling regime carefully. So I mentioned very briefly that the tractor models that I'm discussing are in reality supersymmetric models. And as such, they are constrained by their corresponding supersymmetric phenomenology of the particle physics beyond the standard model. So I'm hoping most of you have heard at least, you know, tangentially about the gravitino problem, no? The case when if supersymmetry is broken well below the scales relevant for inflation, these gravitinos, which are the supersymmetric partner of the graviton particle, are generically and necessarily produced in the primordial plasma during reheating because they have a universal coupling with all of the particles of the standard model, okay? For those gravitinos, the corresponding production rates are suppressed by the gravitational strength of the interaction, but these rates can nevertheless be large enough to overpopulate the universe with gravitinos, or the corresponding light supersymmetric particle, which would correspond to the dark matter particle in these models, to which they would decay. Okay, so recently, I mean last year, there was a new determination of the primordial gravitino abundance, which has a dependence on the decay rate of the inflaton field. Here, M3 stands for the mass of the gravitino, and 1/2 stands for the mass of the gaugino. This is a yield. Let me not address in any detail what it means, but the point is that one can compute the relic abundance, and one can check that this production of gravitinos will overclose the universe unless the Yukawa coupling, that is the effective coupling between the inflaton and matter fields, is less than about 10 to minus 5 for dark matter masses of the order of 100 GeV. If you change the mass, of course, this constraint changes. So we see essentially that reheating we can extract constraints on reheating from observations of the cosmic microwave background. Okay, so of course, as I mentioned, these constraints are model dependent, so you have to fix your inflationary model. But it is, I mean, what one has to do is to forget about doing this naive analysis of, you know, putting 50 and 60 EFOs. You have to actually do the computation of n star properly, and if you do that, you can find non-trivial constraints on the reheating of your inflationary scenarios. Okay. Now, sorry, I'm going back and forth. So this discussion about the bound on reheating from gravitino production, I think, is a very good excuse to start the second part of the lecture, where I want to discuss the way, that we can constrain reheating by looking at the dark sector of the particle theory. Okay. So far, we've only talked about the decay of the inflaton to standard model degrees of freedom. But of course, during reheating, we can also populate the primordial universe with dark relics, with particles that correspond to dark matter or even dark radiation. All right. So, sorry, let me drink a little bit of water. Now, what I'm going to be focusing on is on scenarios where these dark relics, these dark matter is
Excuse
not.
me, Marcos. Yes. So for your gravitino production, yes, this result in the second line, the abundance, depends on the assumption that the supersymmetric particles are lighter than inflaton mass.
Yes.
If I mean supersymmetric particle is heavy,
yes.
What happens? I mean,
if the supersymmetric particle is heavy, then this result changes, and I'm going to mention that in a couple of slides. Yes.
Okay, thank you.
This is a very good question. So yeah, I'm going to be talking now then about the production of dark matter during reheating, and I am going to specialize to one particular family of dark matter models, which corresponds to dark matter that is not equilibrated with the standard model plasma, with the thermal plasma at any time. Okay, so these models are known as freezing models. I forgot to put a slide here making an explicit distinction between freeze out and freezing, as I usually do. The point is that these dark matter particles that I'm going to assume are produced during reheating are very weakly coupled to everything, okay, in particular to all of the standard model. And so even though the standard model thermalizes during reheating and remains in thermal equilibrium for essentially the duration of the age of the universe, these dark matter particles are not going to interact strongly with this thermal plasma, so they are not going to be in thermal equilibrium with themselves or with the visible sector, let's say. Okay. If this is the case, then we can extract some meaningful information about the early universe if, I mean, these particles were to be detected, let's say, because the corresponding phase space distribution of these dark relics will carry then non-trivial information about the dynamics that gave birth to them. Okay, so the phase-space distribution is not washed out and converted into a thermal distribution, but it actually keeps its original shape throughout the age of the universe. In mathematical terms, I think I already showed you twice the definition of the Boltzmann equation in the expanding universe, so I think I can get away with doing this. Okay, in mathematical terms, the absence of equilibrium means that to determine the phase-space distribution of dark matter or its number density, let's say its relic abundance, we need to consider only the forward the forward amplitude of the process, that is from something to dark matter. Okay, it could be inflaton to dark matter, could be standard model particles to dark matter, and the phase-space distribution only of the parent particles. Okay, here we cannot have Bose-Einstein. Well, sorry, we can have it, but there is a subtlety here. So let me not mention it. For now, we're just ignoring the the effects of Bose-Einstein enhancement or Fermi-Dirac suppression on the Boltzmann equation, and we're only going to take information from the phase-space distribution of the parent particles. Okay. In particular, the scenarios that I'm going to consider are known as ultraviolet freezing. I'm going to show what that means in the next slide. And the underlying assumption for this is that as I mentioned, there is a strong segregation between the visible sector, which I'm here showing as, photons, let's say, or any other standard model particle, and the dark sector. Okay, this strong segregation can be originated, for example, from the presence of heavy mediators that communicate the two sectors. One can have coupling suppressed by higher order operators. Think, for example, a vertex that scales with Planck mass, or gravitationally strong interactions. Okay, and in these scenarios, if the relevant ultraviolet scale, let's say from the suppression or from the heavy mediator, which I am denoting generically by lambda, lies above the energy of the involved particles, so let's say above the center of mass energy of the scatterers, if dark matter is produced from a scattering process, then the corresponding effective cross-section is going to be given by a growing function of the center of mass energy, just from dimensional analysis, let's say. So here, this S, this variable S that I'm showing in the amplitude and in the cross-section is the Mandelstam variable S. So it is essentially the square of the center of mass energy. And that means that if this is the case, the production of dark matter will be more efficient at higher energies, which is the same as earlier times. Okay, so that is the point. That's why it's called UV freezing. Again, I will show a drawing in a second. Therefore, if we are producing dark matter very early, then the phase-space distribution of the incoming particles doesn't necessarily have to be that of a thermally equilibrated species. It can be that of the classical condensate. So, for example, the decay of the inflaton into dark matter. As we saw, the phase-space distribution of the inflaton is peaked. Or simply, it could be the phase-space distribution of a not yet equilibrated species if the decoupling time, the decoupling time scale for this process is shorter than the thermalization time for the primordial plasma. Okay, so to be a little bit more clear, I'm going to remind ourselves of this plot, which, as I mentioned before, summarizes the evolution of the early universe. Okay, so here we have cooling down by inflation, reheating begins at the end. We have the oscillation of the inflaton about its minimum, producing matter and radiation, first in a non-equilibrium state until the thermalization timescale that I introduced last time. And after that, the plasma has a definite temperature, but there is a competition between dilution due to expansion and particle creation. Okay, so the temperatures do not redshift as in the entropy conserving case, as I also showed in the previous times, until at the end of reheating, we enter the radiation dominated area and there entropy is conserved, okay? So for the production of non-thermal relics, okay, the energy dependence on the production cross-section, okay, so these cross-sections are assumed to go like E to the N, where E is the center of mass energy. This dependence is going to tell us the moment of time when most of the dark matter is produced. Okay, so here I'm showing the yield. This is essentially how much dark matter we have compared to the background, and here's time. If this power n is less or equal than 1, that is, the cross-section decreases with the energy of the scatterers, then most of the dark matter is going to be produced then at the latest possible times when the universe is the coldest. All right. And in this case, the production shown here as this gray line is going to be saturated essentially near the mass threshold. Okay, at temperatures lower than this value, the production is kinematically forbidden. So we better saturate the observed relic abundance at this moment in time. Okay, so production is happening from below in this plot. Okay, this late time production of dark matter out of equilibrium is known as infrared freezing. So infrared, sorry, because it occurs at low energies. But if sigma, the cross section, grows, well, it's a constant or grows with the center of mass energy, so this n is equal or bigger than 0, the production of dark matter will occur at the highest possible energies, which is the same as the earliest possible times. This is again what I'm calling UV freezing because it happens at high energies, and also means that dark matter is therefore necessarily produced during reheating. Okay, at some point during reheating, at the beginning, in the middle, or at the end, but during reheating. And what we know, and I will elaborate a little bit more later if there is enough time, is that under the assumption of thermal equilibrium, that is, the parent particles are already equilibrated, particle production will be concentrated at the end of reheating if this exponent n is if this exponent n is less than 6. Okay, so essentially what's going on is that if n is less than 6, particles that are produced too soon are diluted by the injection of entropy from the decay of the inflaton, and it is only if the cross-section is extremely steep with an n equal or bigger than 6 that this dilution can be overcome due to the rapid production of particles at early times, and most of the dark matter is produced at the highest possible temperature of the universe, which we correctly identified yesterday. It is the thermalization temperature. Okay. Sorry. This scenario is realized, for example, if dark matter is produced from the collision of particles that are not produced directly from the decay of the inflaton. So let's say the inflaton decays into some particles, but those particles do not scatter to produce dark matter. So to get dark matter, we have to wait until the plasma is thermalized. These new degrees of freedom appear in the background, and then those can scatter and produce dark matter. So we need to wait until we have thermalization. On the other hand, if dark matter can be produced directly from the scattering of inflaton decay products, then, as we saw last time, the mean energy of the particles at very early at the very earliest stage of reheating is of the order of the inflaton mass, which is much higher than the instantaneous temperature. And in such case, dark matter can actually be produced before the complete thermalization of the plasma, despite the fact that the plasma is underpopulated, as we determined yesterday. And in fact, this can happen if this exponent n is bigger than 2. So I'm going to show explicitly some examples later. Okay, one thing I want to mention is that these scenarios can sound very convoluted, very complicated. I mean, how can you even get an exponent that is as big as 6 in the cross section? But it turns out that the literature is essentially full of examples that reproduce several different values of the exponent n. In particular, and this is something that I like a lot, is that one can cover a wide range of possibilities by looking at spin tree hub dark relics. Okay, So one example are supersymmetric models. I mentioned this a little bit before for the case of the light gravitino. Okay, so if the supersymmetry breaking scale is well below the scales relevant for inflation and reheating, as I mentioned, the Planck suppression of the gravitino interactions is going to lead to a production amplitude that in this case scales roughly with the square of the center of mass energy. Okay, so n is equal to 0 for this particular model. Okay, one can also construct minimal non-supersymmetric spin 3 half dark matter models that can couple either to so this dark matter particle can couple to the Higgs and the SU2 charged leptons with a production amplitude that grows with the 4th power of the center of mass energy. So in this case, n is equal to 2. Or they can couple to the abelian gauge boson and right-handed neutrinos, assuming they are present due to the seesaw mechanism. And in this case, the amplitude is steeper because we have a heavy mediator in the middle. So n is equal to 4 for these models, okay? And addressing the question by Professor Hyun-Min, one can have scenarios when the supersymmetry breaking can be extremely large. In fact, it can be larger than the mass of the inflaton with super partners that are heavier than the inflaton itself. And gravitino dark matter in that case can be produced through gauge boson scalar or fermion scatterings with amplitudes that of course are going to be extremely suppressed because you're now interchanging particles that are above the inflationary scale in mass. And in this case, the amplitude grows with the 8th power of the center of mass energy, which is the same cross section that grows with the 6th power of the center of mass energy, okay? So we have n equal to 0, 2, 4, and 6, only considering spin 3 half models, all right? So from the previous, from all of these considerations and what I mentioned in the light of gravitino production when I was discussing the CMB constraint, we can, in a relatively simple way, constrain reheating for these specific models by imposing that the dark matter abundance matches the currently measured value. Okay, so I showed again this for the light gravitino. So for this case, the reheating temperature has to be of the order of 10 to the 9-ish GeV or less. Otherwise, you overclose the universe with dark matter. But what I want to show to you is that we can even go further, okay? The relic abundance is just one data point. We can get another data point by making use of the measurement of the matter power spectrum by the observation of the Lyman-alpha forest to constrain the properties of dark matter and therefore of reheating. And maybe this is a, oh, sorry, no, let me mention this before we stop for the break. Before I do that, yes, it is convenient to introduce some new notation to the lectures. Okay, so we already know that the number density of particles is obtained by integrating the phase space distribution. We are now talking about a very special kind of particles, kind of relics. These are out of equilibrium relics. So these relics are going to be produced through some mechanism, as I said, through decays or through scatterings, up to some point at which this process decouples and the dark matter particle only redshifts after that moment in time. Okay, so for any production mechanism, the computation of the phase space distribution, however we do it numerically or analytically, is necessarily going to involve some characteristic energy scale. I am denoting it here by P0. So this is some energy scale. It can be, for example, the inflaton mass or the reheating temperature or a combination of them or lambda. It's some characteristic energy scale of the problem, okay? And after dark matter decouples at a time that I'm confusingly denoting by T star, sorry, I'm using the notation that is used in the papers, in the literature. The phase space distribution after this time is going to evolve simply following the comoving momentum relative to the coupling. It only gets affected by redshift, essentially. So it depends on this ratio. So it is P divided by P0, but now taking into account expansion, redshift. What one usually does is to introduce the scale factor today in the numerator and the denominator, so that we can rewrite the argument of f in this form. Okay, the numerator is simply the comoving momentum p, so it's p times the scale factor. It is the comoving momentum relative to today. Okay, so it's a divided by a today, and the denominator is nothing but a rescaled characteristic energy scale. Okay, so it's P0 times some number. This number is denoted by T star, and in the literature is also denoted by TNCDM. Okay, NCDM stands for non-cold dark matter for reasons that I'm going to discuss in a minute. Despite the fact that it's not a temperature, as I mentioned, there is no thermal equilibrium associated with these relics. The distribution is not thermal, but I mean, people use it because it is a handy way to mimic the case of neutrinos. Okay, so this was invented for neutrinos. This whole argument in turn is denoted by Q. So it's a rescaled comoving momentum. All right. And as I said, this notation can be a little bit confusing. There is no temperature. We already used Q for the resonance parameter before, but this is the standard notation in literature and most importantly in cosmology code. So if you want to use a cosmology code, you have to use this notation. That's the annoying thing. So I think we can stop now, so I can introduce the Lyman-alpha measurement for warm dark matter and continue with the constraints on reheating from dark matter production.
Okay, thank you. So are there some questions?
Excuse me, I have a question. You mentioned about pre-thermal. I think you divide during the matter era, non-matter era, inflaton domination era, you divided non-thermal epoch and
yes,
thermal, right?
Here, yes.
Yeah, I want to know how to define the distribution function in the non-thermal era. Maybe to calculate the dark matter Boltzmann equation, you need a distribution function.
Yes. So let me try to answer the question in two steps. So the first step is that the distribution function for the inflaton decay products, we computed it yesterday. I don't know if you remember that. We computed it in the perturbative limit and in the non-perturbative regime as well. It was some of the animations that I showed towards the end of the lecture. If you don't remember this, I can show the slides. Do you want me to show the slides or?
Yeah, I remember that discussion.
Okay. So those we computed last time, and it's relatively easy to calculate. Now, with those distributions as a starting point, so let's say this is the Boltzmann equation, so we put here those non-thermal distributions, we can solve the Boltzmann equation and obtain the corresponding distribution for the dark matter particle too. And that is what I'm going to show precisely in the next set of slides. How, well, not exactly how to do it, but what is the result, let's say. But you can do it. In fact, if you put in here the perturbative non-thermal distributions, you can integrate this thing analytically in an exact way, which to me was very surprising. So you can get the exact form of the dark matter phase space distribution if it is produced from pre-thermal scatterings, if that makes sense.
So in the thermal case, maybe we can use just the normal distribution function for the radiation.
Yeah. So as an input here, you can use just the Fermi-Dirac or Bose-Einstein distribution. The distribution for the dark matter particle, though, is not going to be thermal. It is different from thermal. Yes, but yes, that's what one can do.
Okay, so is there any situation we need a distribution function for the pre-thermal era?
Yes, there are situations. For example, here, as I was discussing the high-scale supersymmetry breaking scenario, for example. So In this case, you can produce dark matter in the form of very heavy gravitinos for any initial state, because these particles are coupled universally to the rest of the standard model. So you know, here, as long as the inflaton decays into anything, you're going to produce gravitinos, and the cross section is extremely steep. It scales with the 6th power of the central mass energy, so it's definitely bigger than 2. And you have to worry about that in that scenario.
Okay, thank you.
Yes.
Oh, I have 2 questions. The first one is that is why X plots depends on some details of preheating as well?
Very good question. That's the very last 2 slides I have, I think. So yes, of course, if the particle production is sensitive to the pre-thermal era, then it has to be sensitive to preheating as well. So yes, if you have enough non-perturbative particle production, you can produce essentially all of your dark matter, not just here in this era, but actually here, right at the end of inflation. Yeah, you can. It will happen through the non-perturbative excitation of fields that are coupled to the inflaton. So yeah, preheating is also relevant. I am going to try my best to get to all the way down to the end of this lecture so that we can see that explicitly.
So in this plot, you just consider mainly the perturbative.
Yeah, it's mainly the perturbative case. I mean, this constraint, as I will show the n bigger than 2, this constraint is applies for essentially when you take into account non-perturbative effects, applies for fermionic decay of the inflaton. So the dark matter is produced somewhere in this region. If you have a decay through scalar preheating, then n can be as low as 0 and still be sensitive to the earliest stage of reheating. Yes, but this picture, yes, it's in principle purely perturbative. It is, as I said, it is robust with respect. Well, yeah, it's mostly robust with respect to fermionic preheating, but not so much with respect to scalar preheating.
I see. So just for clarification, so you just don't assume any coupling between inflaton and dark matter here?
No, not here. I am going to assume coupling between the inflaton and dark matter in a few slides as well, because that is going to give us what, to my knowledge, is one of the few model-independent constraints on reheating. So yes, I am going to consider that too. Yes.
As okay, last question. So in the next slide, when the SUSY is broken at high scale, I don't get why it really matter. I mean, if it is broken before the inflation.
Sorry, I didn't get that.
So in this high scale SUSY cases,
yes,
SUSY is broken before the inflation, right?
Well, it's broken at very high scales. Yeah. So in a sense, if you had a bath of particles before inflation started or was efficient, then essentially during inflation, you dilute everything away, including the super partners. But the point is that if they are very heavy, during reheating, you don't regenerate them. You get rid of all of the super partners. They are not present in the plasma ever after the end of inflation. And so the only way you can get them is as virtual particles that mediate essentially these processes. So this big dot is hiding the heavy mediators. So like here, right? So here's where's I don't have very good notation, but you see there is a gluino here, for example. So you would stick, a couple of these diagrams together, and that's why you get 2 gravity in the final state and not just 1, because you can't produce the super partners. The only one that lies below the supersymmetric scale in these models is the gravitino, so it has to be the dark matter.
I see.
Yes.
Yeah, thank you.
Okay, so okay, let's stop. Okay, so let's resume the last part.
Okay, very good. So as I mentioned before, in order to have a better handle on the properties of this out of equilibrium dark matter and of reheating as well, you know, the most data points we have, the better. So one data point is the constraint on the relic abundance measured by, you know, large-scale observations, in particular the CMB, and another data point that we can get is that comes from considerations of the matter power spectrum. And the part of the matter's power spectrum that we are going to be interested in is that can be probed by the observation of the Lyman-alpha forest. So here I'm just showing a snapshot of a video by this fellow that essentially tries to illustrate what is the idea behind this measurement. Okay, so the idea is that very distant quasars emit light that eventually makes our way to us, okay? And this light will excite the Lyman-alpha transition of hydrogen as it traverses over, as it traverses the matter over densities that are present in the intergalactic medium. So the spectral redshift between the reference frame of the quasar and the absorber can tell us the position of the hydrogen cloud along this line of sight, okay? The succession, of emission lines that we get when measuring this intensity of the light is what is known as that particular quasar's Lyman-alpha forest. And the point is that as this relatively old but clear plot shows, Lyman-alpha measurements are essentially the matter power spectrum tracers at scales that are smaller than about 10 megaparsec or so. So very large scales. Of course, we can use the cosmic microwave background itself, but at smaller scales, Lyman-alpha is among the best ways to determine this matter power spectrum. Essentially, what is the distribution of matter at these particular scales, right? Now, you know, if you're a theorist and you want to determine the corresponding power spectrum, the matter power spectrum given a dark matter candidate, then at the linear level, one would study the evolution of the perturbations of the phase space distribution translated into density fluctuations. Remember that the Boltzmann equation that I showed in all these slides was the Boltzmann equation at the background level, at the homogeneous level. But of course, I mean, now we want to track the formation of structure. So the full phase space distribution is of course going to be the homogeneous one, and some extra some perturbations. Okay, so these fluctuations, of course, are going to be now spatially dependent. And they are going to lead to a Boltzmann hierarchy that I'm not writing explicitly here that can be complicated to analyze even numerically. In any case, for a sufficiently non-relativistic species, and I'm going to quantify what that means in a second, this Boltzmann hierarchy that can be written to determine the matter power spectrum can be collapsed into a relatively simple equation for the evolution of what is known the density contrast delta, right? This is the ratio of the matter density fluctuation over the background value. So delta rho divided by rho background. Okay, so that's the density contrast. This is the equation of motion that it satisfies in Fourier space. And if one analyzes this equation, one sees that one has the usual, you know, acceleration friction terms. And one has this piece that depends on the scale k, all right? But this piece is proportional to the equation of state parameter of the corresponding dark matter species, all right? If this dark matter that we're dealing with is perfectly cold, which means it has an exactly vanishing equation of state parameter, then W is equal to 0, this whole term goes away, and this equation loses all the dependence on the scale, meaning the well-known result that overdensities are going to grow democratically and structure forms at essentially all scales. But if this W, this equation of state parameter, is different from 0, that is, dark matter is not perfectly cold, it is not cold, it will have a non-vanishing free streaming velocity that will interfere with the gravitational formation of structure. Okay, so in fact, if one just looks at this equation, one can identify a free streaming scale roughly below which structure will be washed out, essentially. In reality, the correct scale to take, I mean, if one does the analysis more carefully, is given by what is known as the free streaming horizon, which is in any case parametrically related with the free streaming scale. It's not very far away from it, okay? So as one example, for a thermal relic, that is warm dark matter. So a relic that was produced through thermal freeze out. It was in thermal equilibrium at early times and then decoupled from this equilibrium at later times and froze. So that's warm dark matter. The ratio of the power spectrum that one obtains to the power spectrum of a perfectly cold species looks like this, okay? Well, this is the square root of that ratio. This thing is called the transfer function. It is the ratio of the power spectrum to the perfect lambda CDM scenario. It looks like this, okay? So at large scales, they're essentially the same, but there is a cutoff at smaller scales. So this is the washout of structure formation. And in particular, people have looked at this effect beyond the linear order. So of course, this thing that I'm showing here is just a simple, perhaps naive linear computation. I mean, at low scales, we have very non-linear structures in the present universe. So people have looked at this effect, as I said, before the linear order using very expensive and sophisticated n-body simulations. So here are a few examples, okay? So cold dark matter, which is in this bottom, how do you call this thing? This bottom, well, let me call it square. So this is perfect CDM, and you can see you have structure formation and it's grainy. Maybe it would have been better to zoom in a little bit more, but it's grainy. You have structures being formed essentially at any scale. Warm dark matter with a mass equal to 0.5 keV looks very similar, but it has lost the graininess at small scales. You see, this looks like a high definition version of this picture, right? And for hot dark matter with an even lighter species, we obtain only a very blurry result. Okay. Now, a crucial result that was studied in these references is that scales that are relevant for Lyman-alpha today are, of course, very nonlinear, but they were only very mildly so during structure formation. And actually what they find is that any model that can be ruled out via these n-body simulations can also be rejected by doing the simple linear analysis. And in fact, one can go even a little bit further, okay? So, well, before I say that, the current, so I mentioned the measurement from Lyman-alpha of the power spectrum, of course. So the Lyman-alpha bound consists on the fact that so far we have not seen a suppression that looks like this one explicitly in the in this matter power spectrum. So this current lack of observation puts a constraint on the mass of the warm dark matter particle, which is of the order of 3 keV. All right. Now, at the linear level, as I mentioned, the free streaming scale depends only on the nature of dark matter through its equation of state parameter. That, if one computes it, it's related to the first and second moments of the phase space distribution. So the first moment is parameterized by this T star, this effective temperature that I introduced before, and this is the second moment of the distribution. For warm dark matter, this 3 keV bound corresponds to an equation of state parameter today of the order of 10 to the minus 15. So it has to be extremely non-relativistic, okay? And if this is the case, one can check, you know, the consistency that this analysis is valid, okay? So what we suggest to do then is to make use of this very solid constraint, okay, to map it out to any out of equilibrium dark matter model by essentially equating the corresponding equation of state parameters. Okay, so we know what W warm dark matter is, and we know the corresponding bound on the mass. Okay, again, believing that this procedure can be applied for any form of the distribution function, then we can also compute W for another out of equilibrium model, make the two W's equal to each other to determine the free streaming scale, solve for the dark matter mass, and one obtains a let me say universal relation that can tell you what is the lower bound on the dark matter mass if you know the lower bound from observations on a thermalized relic. Okay, the only thing you have to compute are the first two moments of the phase space distribution, but you don't need to input, you don't need to do any numerical computations. You don't need to run any CMB codes. You don't have to do n-body simulations. You don't have to do anything other than this. And this plot shows indeed how this rescaling procedure compares to the warm dark matter bound for I mean, a lot of out of equilibrium models. Okay, we consider a bunch of them, and you can see the matching is pretty good. So we have we have a matching procedure to extract the Lyman-alpha bound given knowing the phase space distribution for the out of equilibrium dark matter. And I think the most obvious case to apply this machinery to begin with is for the simplest scenario. Let's consider the case when the inflaton couples directly to dark matter. So dark matter can be produced from the decay of the inflaton directly. All right. For this case, we already partially know the solution. Okay. Before, at very early times, well before the end of reheating, we found yesterday that the phase space distribution was scaling like the -3/2 power of the momentum with a sharp cutoff at the inflaton mass when we write it in terms of the physical momentum. If we write it in terms of the rescale comoving momentum, the shape is preserved. So here I'm writing, for example, this dashed blue line is evaluated at 0.1 T reheating, so well before the end of reheating. So this Q to the -3/2 shape that I showed yesterday is preserved. It has this sharp cutoff in here. But now, since we're dealing with comoving momentum, the position of this cutoff evolves with time. Okay, so we start here and then it moves to the right, essentially. Now, we obtain that phase space distribution, assuming that it was, assuming that we evaluated at times well before the end of reheating. Okay. But we can now allow, because we're decaying into dark matter that is never going to be in thermal equilibrium, we can now extend this computation until the end of reheating. And to do that, we need to solve the Boltzmann equation with the Dirac delta collision term that I showed yesterday numerically, because we have to take into account now the exponential decay of the inflaton and the transition between matter and radiation domination. So I'm not going to go into the details. The point is that you can calculate this phase space distribution numerically, and it has this form. Okay, so you get some dependence in the reheating parameters and the mass of the inflaton. The characteristic energy scale is essentially related to the present day temperature rescaled by the ratio of the mass of the inflaton to the reheating temperature and by some degrees of freedom. This amplitude, as I said, depends on this ratio, the branching ratio of the decay of the inflaton to dark matter, and the shape of the distribution is this function that I'm showing here. Okay, so at low momentum, as I already keep pointing here, it has the Q to the -3/2 scaling that we obtained in the pre-thermal computation yesterday. But at large momentum, the hard cutoff is replaced by a Gaussian tail. And the key concept here to understand the shape of this distribution is that in the absence of thermal equilibrium, we can read the comoving momentum as if it was a time coordinate in a sense. So initially we have the sharp cutoff, and at the end of inflation, the distribution stops growing because the energy density of the inflaton is now decaying exponentially fast, and so the distribution populates now a tail that gets less and less efficiently populated due to the exponential decay of the inflaton. So we get this non-thermal distribution, which upon integration gives us the well-known, because you can compute this without computing the phase space distribution, the well-known expression for the relic density of dark matter that depends on the dark matter mass, the reheating temperature, the branching ratio of the decay, and the mass of the inflaton. Okay. So as I mentioned before, we can use this expression if we know these two masses to put a constraint on reheating, which is the point of these lectures. But we can do a little bit better, and actually we can make use of this phase space distribution now to determine the Lyman-alpha bound on the mass of the dark matter particle produced through this decay. So if we want does that, if we do that, sorry, we compute the first and second moments of this distribution, substitute them into this equation, we get this corresponding bound, lower bound on the dark matter mass. All right, this bound depends on the ratio of the inflaton mass to the reheating temperature as expected. And for reheating temperatures of the order of 10 to 10 GeV is of the order of 3.8 mega electron volts. So compared to the warm dark matter bound, which was of the keV scale, we have gained 3 orders of magnitude in the bound of the dark matter mass. But as this picture is showing, I mean, this Z, sorry, I didn't change the original picture, but this Z has to be the mass of the inflaton. So this is M5. Okay, as this figure is showing, this bound depends inversely on the reheating temperature. Okay, and this makes sense. Dark matter produced out of equilibrium from the decay of the inflaton is always going to have an energy of the order of 10 to the 13 GeV when it is first produced. So if reheating occurs too early, and therefore T reheating is very large, dark matter is going to have a long time to redshift away its momentum to become cold during structure formation. And so for large reheating temperatures and an inflaton mass of the order of 10 to the 13 GeV, the bound is of the order of a few keV to a few MeV, okay, for very large reheating temperatures. But if reheating occurs too late, then dark matter will not have become non-relativistic during structure formation unless it is extremely massive. And in fact, near the VBN limit, we need it to be to have a mass of the order of 10 to the 9 GeV to avoid the power spectrum constraint. Okay, so you can see this Lyman-alpha constraint covers a wide range of masses. And one thing that I consider to be quite important, I mean, I think it is important, is that if we combine this bound with the bound on the relic abundance, we can put an absolute bound on the branching ratio for the decay of the inflaton into dark matter during reheating, which can never be bigger than 10 to the minus 4. Okay, so this bound doesn't depend at all on the model. This one is absolute. It's one of the few model independent bounds that I am aware of that apply for reheating. All right. Now, in the case, I had this extra additional plot. So I was mentioning the direct decay of the inflaton to dark matter via the perturbative process. If one considers preheating, for example, the 4-legged vertex that I was showing yesterday, one can in principle calculate the corresponding bound. So if we are in the weakly coupled regime, the phase space distribution can be calculated. I showed it yesterday. And if one computes the Lyman-alpha bound, one sees that the opposite happens. If we have scalar preheating, that is the decay of the inflaton to dark matter proceeds not through the 3-legged vertex, but through the 4-legged vertex, the dark matter bound is very small. You can have extremely small, extremely light dark matter particles of the order of a few eV, a few electron volts, and still satisfy the Lyman-alpha bound. But this is perturbative. For non-perturbative inflaton decay to dark matter, we are not there yet. We're preparing actually a paper on that. So let me go now very quickly to the case of not direct decay, but of scatterings of the inflaton to for not of the inflaton, sorry, to the case of dark matter production through scatterings of particles that are present in the primordial reheating plasma. Okay, and let me begin by the case where the parent particles are already in thermal equilibrium.
Marcos, excuse
Yes.
me, I'm a bit confused about the case perturbative. I mean, you can see the perturbative cases.
Yes.
Inflaton condensate, and what is the second part? This small mass bound.
Oh, the small mass bound. Yeah.
Where does it come from?
So this first bound comes from essentially. We can separate it into two cases to make the discussion a little bit easier. Let's assume that the decay of the inflaton produces fermionic dark matter. Okay, so it happens through the Yukawa coupling. Then, if that is the case, the phase space distribution that I was drawing yesterday, or this one, is at the end of reheating. Okay, so the Lyman-alpha constraint depends on what happens at the very end of reheating. So hence the dependence on the reheating temperature. And so the bound can be as small as a few keV if the reheating temperature is very large, or can be as big as 10 to the 9 G electron volts if the reheating temperature is very low. But if you produce, for example, scalar dark matter through the phi square chi square interaction, then the phase space distribution that for some reason I didn't put in this slide, but it's in the it is in the slides. It is peaked at the earliest possible times. Dark matter will be produced essentially at the very beginning of reheating, not at the end, but at the beginning. And I'm going to show that also a little bit more explicitly for scatterings in a few slides. But it happens at the beginning of reheating. So in that case, the Lyman-alpha constraint doesn't care at all about the reheating temperature. I mean, how long reheating lasts? Who cares? Because the dark matter is produced at the very end of inflation. And that means that the Lyman-alpha bound gets weakened because the dark matter particle, sorry, I'm disconnecting this phone. The dark matter particle has a lot of time to redshift away its momentum from the end of inflation to the structure formation era. Okay. So this result, what I'm saying is that applies on the weak coupling regime. For the non-perturbative regime for preheating, I don't have an answer yet. So maybe in a month. So that's the point. These are two different production scenarios. I'm hoping the preheating case is going to be a little bit more clear in a few slides when I combine it with the scatterings. Okay, so I still have a few slides to go through.
The only spin dependent. Okay.
Yeah. So this one is kind of a spin dependence. Exactly.
Thank you.
Exactly. Now, for thermal freezing, that is the dark matter is produced through the scattering of thermalized particles. I mentioned earlier that for n less than 6, although the production of dark matter at the early stages of reheating can be enhanced by high temperatures, can be enhanced by high temperatures, the continuous injection of entropy from the decay of the inflaton will be more efficient at diluting any primordial population. And so dark matter decouples at the very end of reheating. So the relic abundance, forgive these horrible coefficients, the relic abundance depends only on the reheating. On the other hand, for n equal or bigger than 6, the enhanced production rate wins over the dilution effect, and dark matter can become a relic of the earliest stages of reheating. If we assume instantaneous thermalization, it will become dependent on Tmax. If we don't assume instantaneous thermalization, then you replace this Tmax by T thermalization, the one that we computed yesterday. And this effect can also be seen in the corresponding phase space distributions. For n less than 6, it turns out that the distributions are have a single peak, essentially, with an exponential tail. So all of them can be parameterized in this way. These alphas and betas and gammas have to be fitted to the numerical solution. I'm showing 3 lines because the final state, sorry, the initial state can be a pair of bosons, or it can be a fermion and a boson, or it can be 2 fermions, and that affects the form of the phase space distribution. But for all these cases, there is an exponential tail that is reminiscent of the thermal progenitors, and but the distributions themselves are not exactly thermal. Okay, but the rescaling, sorry, the characteristic energy scale is related only to the present temperature. So one would expect the Lyman-alpha constraint to be not very different from that of a warm dark matter relic. But for a higher n, for example, n equals to 6 in here, the phase space distribution is actually much more complicated. As I said before, if we read Q kind of like a time variable, what happens is that at the beginning of reheating, there is a sharp rise in the distribution with a peak related precisely to the value of Tmax. And then a power law, a power-like plateau appears coming from the competition between production and dilution during reheating, until at the end of reheating, an exponential drop-off appears. So for these models, the Lyman-alpha constraint can be a little bit boring, again, depending on the steepness of the cross-section. For n equals to n less than 6, the bound is only marginally larger than the warm dark matter one. Instead of being 3 keV, is 8 keV, let's say. And that's because the distribution is not very far from a thermal one. It's not thermal, but it's close enough. But for larger n, the bound depends on the ratio of Tmax to T reheating. So again, we can put constraints on the couplings during reheating by looking at this bound. This ratio is in general, well, the ratio of T reheating to Tmax is in general much less than 1, meaning that the bound is weakened. Dark matter decouples, as I mentioned in the preheating case, very early during reheating, and now has the full duration of reheating and of radiation domination to become sufficiently non-relativistic. And one can actually draw some exclusion contours. Let me skip this part, it's not very interesting. Because things are more interesting if dark matter is produced before the complete thermalization of the primordial plasma. Okay, so as I mentioned earlier, this can happen if the scattering cross-section grows faster than the second power of the center of mass energy, if the inflaton decay products are directly responsible for producing the dark matter particles. Okay, so here's a plot. This R is the ratio of the non-thermal yield to the thermal yield. So for n bigger than 2, essentially, non-thermal yield wins. And that's the case of the high-scale SUSY scenario. Whereas for low-scale SUSY, the thermal one wins. Okay. The relic abundance can be computed in general. I'm not showing the horrible prefactors here. The only thing I want to emphasize is that this relic abundance will not depend only on the reheating temperature and the inflaton mass, and of course the UV scale, but it will be sensitive to the thermalization timescale. This is very important. So now we need to know when the plasma is thermalized to compute the correct relic abundance. And of course, as you can imagine, for this non-thermal freezing scenario, the phase space distribution has to be computed on a case-by-case basis. We don't have thermal equilibrium. So in particular, if the pre-thermal scattering parent particles are produced perturbatively, the distribution can be computed exactly, and for the case n equals to 4, it looks like this. Okay, so one obtains a very horrible expression for the prefactors, precisely because of the phony dependence of the thermalization timescale on the gauge coupling and the reheating temperature and the inflaton mass. Okay, but one can write it down, one can solve the Boltzmann equation exactly, and one can fit it with a slightly simpler expression that looks like this. So the distribution, again, is non-thermal. It inherits the q to the -3½ power behavior of the not yet thermalized decay products of the inflaton, but it has a tail that decays faster than a Gaussian. Okay, and let me see, to illustrate the interplay, and the Lyman-alpha constraint in turn can also be computed. It is also weakened with respect to the warm dark matter bound because dark matter is the coupling in this case at thermalization. Okay, so to illustrate the interplay of these constraints, I think it's a good idea to look at the particular model. Here I selected it to be one of the non-supersymmetric spin 3/2 scenarios that I introduce later, where n equals to 4 is realized. So depending on the branching ratio of the inflaton to the Higgs or to the neutrino, for example, here the branching ratio is chosen to be 10 to the minus 4 for the neutrino, the parameter space that is spanned by the mass of the dark matter and the reheating temperature splits in two. In the white region of the parameter space at large reheating temperatures, dark matter production is dominated by thermal freezing, making this dark matter a relic of the end of reheating, whereas for low reheating temperatures, the production is dominated by non-thermal freezing, making dark matter a relic of the end of inflation, essentially. And these lines here correspond to the observed relic abundance as a function of the dark matter and the matter coupling. Okay, so we can have thermal or non-thermal production depending again on the dynamics during reheating. Now we can do the opposite. We can actually obtain information about reheating if we can measure if we can detect a dark matter like this one. So this exclusion region in blue corresponds to the limits of the lifetime of this dark matter, because it's in general unstable as given by gamma ray and neutrino constraints. So here I'm signaling the Fermi 130 GeV event or the IceCube PeV event, just to emphasize the fact that if one gets a signal, you can translate it to a particular reheating temperature and to the corresponding production mechanism, which I think is very interesting. The exclusion region to the left is the Lyman-alpha bound. And you see it is trivial in the thermal freezing case, but it is less than trivial in the non-thermal freezing case because it depends on the thermalization timescale. This right panel is a little bit more extreme. It corresponds to the case when dark matter is produced directly from the decay of the inflaton. And if that is the case, Lyman-alpha excludes all of the parameter space except for very large reheating temperatures or sufficiently large dark matter masses. Okay. Now I can finish with the last slides where I take into account the non-perturbative particle production, which seems to be the most interesting case for people in the audience. So if one does that, the picture can change actually significantly. Okay, so to clarify as much as possible what I'm showing here, what I'm considering now is the production of dark matter from the scattering of particles in the primordial plasma, where these particles that scatter are produced via a non-perturbative decay of the inflaton field. Okay, so in this case, phi decays non-perturbatively into a pair of fermions, and these pair of fermions, when they collide, they will produce dark matter. So it's like a chain of events. Okay. So what I'm showing here as these 6 panels is the result of the computation of the comoving dark matter number density. So it's n times a cubed, that's the comoving number density, as a function of the scale factor during reheating. Okay, comparing the production, comparing the particle production from the non-perturbative computation to the perturbative result using the Boltzmann equation, and also comparing it to the naive thermal expectation. We know that at early times there is no thermalization, but just for comparison, I'm showing it here, okay? And I am doing this for weak coupling and strong coupling. So weak coupling is the first row, strong coupling is the second row, for cross sections that grow with the second, fourth, and sixth power of the center of mass energy. So those are codified in the columns, okay? So if we start at small coupling, one can see that the non-perturbative the non-thermal, by the way, the orange line is not just perturbative, it is the non-thermal perturbative computation. So it is as correct as one can get using the Boltzmann equation. Okay, so this one is non-thermal, but it is perturbative. And we see that it matches very well the full non-perturbative computation for n equals to 2. Okay, but if we consider steeper cross sections, the initial burst of particle production that I showed a few slides ago, maybe I can go back actually very quickly, just hoping this thing doesn't crash. Is here. Okay, so if we are in the strong coupling regime, we have first a large burst of particle production, and then we see the Pauli suppression coming from the Fermi-Dirac statistics. If the cross-section is very steep, then that manifests here as a as a very efficient stage of dark matter production. Okay, so for n equals to 4, the non-perturbative computation tells us that we get more dark matter produced at early stages than if we just do the full Boltzmann computation. And in the n equals to 6 case, this is even more extreme. I mean, at the beginning of reheating, we get an enhancement of several orders of magnitude. Let me not count the numbers in here. Okay. Now, sorry, yes. So these results then in that, yeah, good point here. So for n equals to 2, we see two things. So one was the matching between perturbative and non-perturbative, but the other thing that we see here is that the thermal assumption has the same slope as the other two, okay? It is smaller, but it has the same slope. Now, these co-moving number densities are growing with time. They grow with the scale factor. Eventually, the primordial plasma is going to be thermalized. And so this non-thermal production channel is going to shut off, and the thermal production channel eventually is going to catch up with this abundance. And at the end of the day, for n equals to 2, thermal production is going to end up deciding the amount of dark matter that is present in the universe at the end of reheating. Okay, so that's for n equals to 2. For n equals to 4 or 6, we see that the slope of the thermal approximation is much shallower, and this is consistent with the observation that I made a few slides ago, that if n is bigger than 2, then the dark matter production is determined exclusively before the complete thermalization of the primordial plasma. But we can see here that we can get an even stronger effect, that actually non-perturbative, non-thermal effects can determine the dark matter abundance. And that can be a little bit more extreme in the large coupling regime. For n equals to 2, we see that this number density essentially mimics the behavior of the energy density of fermions. It is initially very large compared to the perturbative result, but it then becomes suppressed by the Pauli blocking. But these two curves eventually merge with each other. And at the end of the day, this non-perturbative effect won't leave a long-lasting mark in the dark matter relic abundance, because the thermal computation is eventually going to catch up after thermalization. But for larger n, despite this Pauli blocking, the production of dark matter, as I mentioned, can be much more efficient than assuming the perturbative dynamics. So here we see that, again, the difference for the relic abundance can be of a few orders of magnitude. So this fermionic scenario is a little bit complicated because it depends on the thermalization timescale. And so I think it's a good idea to summarize these results with a diagram. Okay, so if we have fermionic preheating, initially the non-perturbative dynamics will dominate. Okay, but eventually Pauli blocking is going to go away. Not Pauli blocking, the resonant effect is going to go away, and the perturbative description is going to take over. Okay, so we see here the evolution of the number density. For the non-perturbative, it just plateaus. Perturbative description takes over. It grows like the 3/2 power of the scale factor. And now, depending on how steep the cross-section is for the dark matter production, the relic abundance may be set at the end of reheating by thermal production, or it might be set at the thermalization time well before the end of reheating. So one has to look at the diagram like this one to decide, you know, what is the case when one has non-perturbative production of fermions. On the other hand, if we have scalar preheating, the results are much more clear-cut, okay? Because first of all, well, here I'm showing now 4 lines, okay? So again, this is weak coupling and this is strong coupling. So I'm showing 4 lines because the black one is a stable, stable scalar field that is non-perturbatively produced through preheating. The dashed line is an unstable scalar field produced non-perturbatively during preheating. The dotted dash curve is the perturbative computation, the non-thermal one, and the dotted one is the perturbative thermal computation. Okay, so I was saying this just because I wanted to say that in every single case you see thermal production is completely negligible. Okay, so if we have scalar preheating and we have dark matter coupled to the field that is non-perturbatively excited, we can forget about doing the computation thermally. Okay. Now, if the coupling is small and the power is not very large, in this case n equals to 2, the perturbative estimation you can see is a very good estimate to the final dark matter relic abundance. And also the unstable scalar field leads to a very similar end result. The fact that the comoving number density plateaus means that as soon as we reach this value, dark matter production has stopped. So we get all of the dark matter, essentially just a couple of oscillations after the end of inflation. For steeper cross sections, the non-perturbative particle production, though, can lead to a more efficient production of dark matter with respect to the perturbative calculation in the n equals to 6 case by about 1 order of magnitude. Okay, so you have to do the preheating analysis to determine the dark matter relic abundance. For large coupling, of course, the effect of the parametric resonance or the enhanced decay of the unstable scalar particle are going to be very clearly present. So for n equals to 2, we can see that the dark matter relic abundance is growing almost discretely because the chi field is passing through the resonance bands, and we get an enhancement relative to the perturbative computation of about 3 orders of magnitude. Okay. And in the case that this chi field is unstable, the dark matter abundance is actually suppressed by also by about wait, why did I say 3 orders of magnitude? It's a lot more than that, right? Well, in any case, this one is enhanced by a few orders of magnitude. This one is suppressed by less orders of magnitude, but it's suppressed as well. How many it is like 4 orders of magnitude, right? Okay, so that's for n equals to 2. If we keep increasing the value of n, we see that the separation between the perturbative computation and, sorry, the perturbative computation, the orange one, and the non-perturbative one, the black one, just keeps growing. Okay, so if you have n equals to 6, the difference is gigantic. Okay. And even the unstable scalar field can lead to much more dark matter production than assuming, well, than what you would compute by integrating the Boltzmann equation. Okay, so this leads then to we can see that this difference in the black and the dashed lines can lead to a very different parameter space for the stable and the unstable cases. Okay. If we assume, let's say for definiteness, that the UV scale parameterized by lambda is of the order of 10 to the 14 GeV, and a reheating temperature, where is the reheating temperature here, of around 10 to the 10 GeV, the range of masses that we need to saturate the observed relic abundance for the stable scalar field case has a very wide range depending on the coupling. It goes from 10 to the 13 GeV, as massive as the inflaton field, all the way down to the sub-electron volt range. Okay. On the other hand, if this chi field that is parametrically excited is unstable, the connection between the mass and the coupling is not one-to-one, because increasing the coupling decreases the amount of radiation. So we can only produce so we can only have dark matter masses that are bigger than essentially 10 to the 3 GeV. And unfortunately, there are no Lyman-alpha constraints yet for these kind of scenarios. So I have 0 minutes. I can stop here. Let me just mention extremely quickly that these last two plots that I had for k equals to 2, for k bigger than 2 for non-quadratic potentials, one can also compute constraints on freezing for dark matter for dark matter from inflaton decay or for thermal freezing. In this case, as one would expect, the results depend on the shape of the potential, but you can read these in the references. So this is the very last slide that I have, and just to summarize, all I want to say is that, of course, if we can understand reheating, we can understand the Big Bang, essentially. By old, I mean this idea that during the Big Bang, matter and radiation are produced. Well, that's precisely reheating. Now, in the context of this last lecture, given a UV model, reheating is getting more and more constrained, either from CMB observations or from some alternative probes, such as dark relics. Of course, I didn't have time to talk about other things that happen during reheating, like phase transitions, baryogenesis, the production of gravitational waves, or the production of primordial black holes. But in any case, I sincerely hope that you have learned a lot from these lectures. Thank you so much.
Okay, thank you very much for your nice lectures from Monday until today. Yeah, so maybe there might be some questions for this lecture.
May I ask 2 questions?
Sure.
Thank you very much. First question is in the non-perturbative, non-thermal freezing.
Yes.
Yeah. This is the inflaton decay into the dark mediator, and the dark mediator make the dark matter.
In a sense, yes.
In this case, this mediator should not enoughly interact with the standard model particles. It should be dark.
It is not a problem, actually. So the mediator doesn't have to be dark. The only thing that has to be dark is the dark matter. So the reason why, and I forgot to mention this, the reason why I keep insisting on having an unstable mediator, let's say, is because if you identify the scalar particle with the Higgs field, for example, then the Higgs, of course, has a very large Yukawa coupling to other particles, in particular to the top quark, right? So it is going to be unstable, and therefore one has to study that effect as well. You can have inflaton to Higgs to dark matter, and then this would be the result. Not this one, the big one, but the dashed one, if that makes sense.
So the mediator can be the summer?
The mediator can be, sorry, what?
So, for example, if Kai is a Higgs field itself can be the thermal.
Yes. The Higgs field can be thermal. So, point here is that if we can non-perturbatively excite the Higgs field, the dark matter abundance is set well before the Higgs has time to thermalize, because the thermalization timescale is all the way to the right. If that doesn't happen, and for example, the Higgs is only produced after thermalization, so it is necessarily in thermal equilibrium, then one has to look at this case, the thermal freezing scenario, which is a lot easier, of course, because the result depends only, I mean, the Lyman-alpha constraint, for example, doesn't care about the reheating temperature unless you're in these cases. And the phase space distributions are very close to being thermal. So you can compute the relic abundance, I mean, in 10 minutes. It's a very simple exercise.
I see. So the different from the different from the final picture.
Yes.
If it's I see. Thank you very much.
Yes. So it depends. I mean, if the Higgs can thermalize, you use this expression. If it doesn't thermalize quickly because it's non-perturbatively produced, so it takes time for it to reach thermal equilibrium, then you have to look at this effect. That's the gist of it.
Thank you very much. Second question is in your slide of perturbative decay of oscillating condensate.
Yes.
Yeah. So there's some
Here.
Yeah, this one. So in relic density, the inflaton mass is in the denominator.
Yes.
Yeah. So first I thought that if inflaton mass is large, the decay width is large, so that relic density becomes large. But the inflaton mass is in the denominator. So maybe
yes. This is a very good point. Actually, there is another inflaton mass hidden in the reheating temperature. Because the width also depends on the inflaton mass. So at the end of the day, I think you still are going to have it probably in the denominator, but with a different power. So let me think. Can you repeat the question? Sorry.
Yeah. I thought that the decay width becomes large if the inflaton mass is large.
Yes.
Then inflaton, so that the decay width is large, so that the dark matter production becomes more large. But
yes.
maybe the dark matter distribution also maybe depends on the inflaton mass.
Okay. I think I see the point. Yes. So if you, Okay. So this is related to what I was saying. Let me put it in this way. The effect that you're talking about, that if you increase the inflaton mass, the width increases, is hidden here in the reheating temperature. So yes. The reheating temperature depends also on the inflaton mass. If you make an assumption about the coupling of the inflaton to dark matter, so it's hidden in here. In some cases, I was using the Yukawa coupling Y because that one is independent of the mass of the inflaton, but the reheating temperature is not independent of it. It depends also on the mass of the inflaton. If you assume. It depends on what kind of width you assume. So if the dark matter is a fermion, then the width is proportional to the mass of the inflaton. If the dark matter is a boson, for example, that is produced through the trilinear vertex, then the inflaton mass goes in the denominator of the width. So if you increase the mass, then the width is decreased. So in this context, it's a little bit better to write it in terms of the reheating temperature, because this is more general, let's say.
Okay, thank you very much.
Okay. Tongmok, you have a question?
Thank you for a very nice lecture. I learned really a lot. And one live question is that, as you mentioned, for the fermionic preheating,
yes,
it seems that there is some problems with lattice simulation, right? But on your results on such a fermionic production from the preheating, did you?
Oh, sorry, not here. Sorry.
Any results? I mean,
the energy densities. You mean that was?
For example.
Here, yes.
Right. So, how do you implement on these? Isn't it from the lattice simulation, or just you concentrate only on the early time without considering the back reaction?
So what you're asking is a very good point, in the sense that first of all, yes, to derive these results, as you can see, judging by the range of values spanned by the scale factor, I was just focusing on early times, very early times, in a sense, to compare the production of fermions from the decay of the inflaton, the non-perturbative production of fermions from the inflaton to the perturbative case. So in that sense, if you're in this regime, okay, there is no difference, and you can get away with just computing things perturbatively. If the coupling is sufficiently large, then yes, it depends. So if you make this Y even bigger, then you have to track the evolution of this energy density to much later times. The problem is that here we were using what is called as a spectral integrator, let's say. So you look at the Fourier transform, at the at the momentum modes of the fermionic field. And as you can see from this right panel that shows the occupation number of the fermion, it contains a lot of oscillations, and numerically it is very hard to solve systems that oscillate with a very high frequency, and these frequencies increase as the running time increases, because the momentum modes are cascading towards the ultraviolet, so they have very short wavelengths. That is the issue. So we stopped at couplings that were not extremely high. So you're asking about the lattice simulation. The problem is that the lattice simulation is available only for scalar fields, because you're solving the classical equations of motion. So you would have to develop a lattice code that has an input of, Grassmann variables or spinors, if you wish, to be able to solve the Dirac equation in the expanding universe. That is the problem with the fermions. So I am aware that there is at least one piece of work in the literature where people don't compute the evolution of the field directly, but they compute the evolution of expectation values of the field. Mm-hmm. So those expectation values are scalars, and therefore you can track them classically. But the paper they wrote doesn't have a lot of details about the evolution, for example, of energy densities. So I personally haven't used that code. I don't even know if the code is available. I know the paper exists, but I don't know if the code, you can just use it. Maybe yes, maybe not. But I am not sure if you can apply it to this kind of problem. Okay, maybe you can just compute some certain kinds of correlators, or maybe just the occupation numbers, and then you have to do all the work to also compute these things. All I know is that, at least, and that's what I wanted to say here, that for CMB observables, preheating is irrelevant if it is fermionic. Okay, that's the whole thing.
I see. Yeah, thank you.
Okay, is there further questions? Okay, I think that we have learned a lot from these lectures. I think the Marcos made a lot of effort to make these lectures successful and more attractable, right? So thank you for your giving these lectures and giving this opportunity to all of us. And I think that will be the base for the future research, right? So
yes.
you have given a lot of materials, and we need to digest all the content.
Yes.
Can go back to the first two lectures and remind ourselves. And if you have any questions from the audience, you can ask directly to Marcos.
Yes.
I think Marcos is a very kind person, and he could reply kindly to all the questions.
Yes.
I
was precisely going to say that if any of you are interested in talking further about any of these topics, then just send me an email and we can set up something.
Yeah, in the future maybe we can put the formulas on the lattice.
Oh yes.
Maybe
yes. So as I said, right now you have to be careful. You can burn your computer.
You need supercomputer.
Yes. You need something more.
Okay, thank you for your from the theory to observations in these lectures. Thank you for your lectures.
No,
okay.
Thank you for the invitation. Thank you so
much.
Thank
you to all the participants. Okay, see you next time. Maybe we can see each other again. Marcos, see you.
Yes.